In this lesson, we're going to talk about combining functions symbolically with the operations of addition, subtraction, multiplication, and division. When we see this notation f plus g of x, that function notation, we're going to combine the functions with addition, just do f of x plus g of x. Same with subtraction, multiplication, and division. It's important to understand the actual function notation. That does not mean that we are multiplying by x. It just means that that's the input for this specific function, the new function that has the operation. We're also going to focus on the domain, but we'll look at that here in just a second. So in this first one, we're going to compute f plus g. It can be written as f plus g, but typically we're going to need that function notation part. So it will say of x. F plus g of x would mean we have our f function, the square root of x minus 2, and we're combining it with g, the square root of 7 minus x. We're using that operation of addition. So now we just have f plus g. If we can simplify this, we will, but we cannot combine these two square roots since they don't have the same radicand. But let's consider, what does the domain of that function look like? When we're considering any function operation, we need to think about the domains individually and then how that operation will affect the overlap of these two domains. So let's think about the domain of f. F of x is a square root function, so it does bring domain restrictions because I can't square root a negative. So the inside of the square root has to be greater than or equal to 0. Well, the inside here is x minus 2, which tells us that x has to be greater than or equal to 2. If we consider the domain of g, it's also a square root function. So it still cannot square root a negative. The inside of that square root must be greater than or equal to 0. And we have 7 minus x must be greater than or equal to 0. We solve that inequality. You can subtract x, divide by -1, flips our inequality sign, and makes that x is less than or equal to 7. When we consider both of these domains together, we're going to find 2 on our number line, and we're including 2 since it can equal 2. And we want numbers that are greater than 2. However, we also have this restriction that it has to be less than or equal to 7. That means it can equal 7, we're going to include that, but it's also less than 7 to the left. So we're shading in the numbers between 2 and 7. That means the domain of f plus g would look like bracket 2 all the way to 7, closing bracket. As we look at the second one, we have two functions that are both quadratic. We're going to do f minus g. So f minus g of x would be equal to, and let's start out with f as x squared minus 5x plus 3. And our g function is 2x squared minus 11x minus 14. So f minus g would mean we are subtracting the 2. The order of subtraction matters. But also the way you write it matters. Right now, I would be getting my problem incorrect because I'm only subtracting that 2x squared. We would need to clarify that we're subtracting all of g of x. You can put parentheses around f of x there. These parentheses don't really do anything because we're not distributing anything to it, but sometimes people like to put them there just to organize their work. So we end up with x squared minus 5x plus 3. We're subtracting 2x squared. Subtracting a negative 11 makes that plus 11x. And subtracting a negative 14 makes that plus 14. If we can simplify, we will. So we simplify and combine like terms. We get a negative x squared. Negative 5x and 11x makes positive 6x. And 3 and 14 makes 17. This is as simplified as this function is going to get. One thing that I recommend, and really encourage you to do is to make sure that you're bringing down this function notation, because a lot of people get confused when they're writing their equals or they're not keeping their work organized. They don't pay attention to what should be on the left side of this equation, because it's not really just an equation, we're writing a function. If we consider the domains of these functions, f is a quadratic function, so it doesn't have any domain restrictions. Its domain's negative infinity to infinity. Well, so is g. It's also a quadratic. If I was to combine those domains, it's still going to be negative infinity to infinity. So the domain of f minus g is negative infinity to infinity. We have several functions that we can work with, and so work through whatever examples you need. We're going to have f times g. F of x is negative 8x plus 9, so if I did f times g of x, my f of x function, I'll write here in blue, and g is here in pink, but we are multiplying these two things together. If I just put a single dot, the only thing that's being multiplied is 9 and 3. So we're clarifying that we're multiplying all of f times all of g, which means I'm going to need to distribute this out. We'll get negative 8x times 3x is negative 24x. Negative 8 and negative 2 makes a positive 16x. 9 and 3x is 27x. And 9 and negative 2 is negative 18. We still combine what we can. I'm sorry, that should be a negative 24x squared. So that leaves me with negative 24x squared. 16x and 27x combines to be 43x, and then minus 18. That's as simplified as it's going to get. Remember to bring down your function notation. That just keeps everything organized and you'll make less mistakes. But when we think about its domain, the domain of f, it's a linear function. There are no square roots, there are no rationals in it, so it's still negative infinity to infinity. G is also linear, so the overlap of those domains, the domain of fg would still be negative infinity to infinity. 4, we have a rational function, so we know that we're going to bring in some restrictions. We want to compute f minus g. F minus g would mean I'm going to start with f. We've got 4x minus 1 over x plus 2. And we're subtracting our g of x, which is x squared minus 25. So we want to make sure that we're showing we're subtracting the entire function g of x. To simplify this, we're going to distribute that subtraction. So minus x squared and plus 25. And I'm going to leave it like that. Right now, that's all we can do to simplify this. We haven't talked about how do I combine rational expressions, needing to get a common denominator and stuff. So unless you're using some outside resource to help you with this, this is what you would end up as your answer. Now the domain of f, we already mentioned, will have restrictions because it is a rational function. In any rational, that denominator cannot equal 0. We know that because I can't divide by 0. So if the denominator is x plus 2, that would mean that x cannot be negative 2. G did not bring in any restrictions. G was a quadratic function, so its domain was negative infinity to infinity. If we think about the overlap of these two functions, the overlap of these two domains, negative 2 is still going to be removed, but every other number works. So if I look at that domain of f minus g, it would be negative infinity up to negative 2 union negative 2 to infinity. So the only number is that negative 2 that's been removed. F divided by g says our f of x is on top. So we're going to have x plus 8 on top over g of x, 5x squared minus x minus 4. When I think about this operation, now we have division. This division didn't exist already, but because we're doing an operation of division, now we've made this fraction that is going to have a denominator. So if you think about the domain of f, it was linear, it's negative infinity to infinity. The domain of g was a quadratic, so it should be negative infinity to infinity. However, because we're doing division, the denominator of that fraction cannot equal 0. G of x is the denominator, so we're going to say 5x squared minus x minus 4 cannot be 0. Looking at this, we see it's a quadratic equation, and right now we're factoring, so we're going to factor this quadratic. So 5x squared came from 5x times x, and then you look for your other factors that would give you 4. So I'm going to try 4 and 1. If I do that on the inside, I get 4x, and on the outside, we get 5x. That can combine to give me a negative x if it was a negative 5x and a positive 4x. So this is our factored form. We set each factor equal to 0. And I'm running out of room here, but you would subtract your 4 and then divide by 5, which makes this negative 4/5. X minus 1 can't be 0, which means x can't be 1. So those are the two values that will be removed from that domain. And you can draw a number line. Negative 4/5 is going to be somewhere below positive 1, but both of them are removed. That can't be those two values. So they're going to be open circles. And then we shade everywhere else. So the domain of f divided by g would say negative infinity up to negative 4/5 union negative 4/5 up to 1, and then union 1 to infinity. There's no way that we can really simplify this fraction. The only way that we reduce fractions is by finding a common factor to reduce. And if I did put this in factored form, that denominator would have said 5x plus 4, x minus 1, which doesn't give us a common factor. So you can leave it like this. In number 6, we're still doing division. So we have f divided by g of x. So we're going to make sure we have that function notation. F is going on top, which is 2 plus the square root of x minus 1. Automatically, I know that's going to have restrictions because it has a square root somewhere. Divided by g, so 2x squared minus 7x minus 30. Again, we're not going to be able to simplify this any further. But when we think about the domain of f, it has a square root in it, so we know that the inside of the square root has to be greater than or equal to 0. The inside's x minus 3, so that would tell us that x has to be greater than or equal to 3. G was a quadratic function, so it did not normally have restrictions. It would have been negative infinity to infinity. However, we put g in the denominator of a fraction. So now we also know that the denominator cannot be 0. Anytime you're doing f divided by g or the division of two functions in general, it will create that restriction where the denominator cannot equal 0, no matter what's in that denominator. You just determine when would that happen. So to figure out when this denominator equals 0, we're going to factor it again. There's no GCF, so we go straight to 2x times x. We find factors of 30 that's going to combine somehow. So we get 6 and 5 here. Inside, that's 5x. Outside is 6 times 2x, so 12x. 5x and 12x can give me a negative 7x if it was a negative 12x and positive 5x. So there's our factored form. We would set each factor equal to 0 using that zero product property, which tells me negative 5/2 and positive 6 are going to be removed from the domain. If you want to draw a number line, I'm going to find negative 5/2 and positive 6 and remove those. However, that was not the only domain restriction. So a lot of times we get stuck into that pattern of finding the denominator, but we also had an issue in the numerator because there was a square root. So we need to consider the fact that f is still going to have those domain restrictions. So we find 3, which is somewhere between negative 5/2 and 6. And we're saying that x can be greater than or equal to 3, so we're going to include 3 and shade to the right. As I'm shading, we still can't equal 6, but we're going to go past 6. So really that negative 5/2 doesn't matter because it would not have worked in that square root function anyway. So the domain of f divided by g here would say bracket 3, because there's our lowest point, all the way up to 6. We're removing 6, so it's going to be a parentheses there, and then 6 to infinity. Number 7, we have f divided by g again. So we're going to put f of x on top, x squared plus 3x minus 40. And it's over g of x. Well, g of x is this square root function, 2x minus 1. So not only do we know that we have this square root issue, but also we created division, so the denominator is going to be a problem. When we think about the domain of f, it was negative infinity to infinity. But the domain of g said that the inside of a square root has to be greater than or equal to 0. So if we said 2x minus 1 was greater than or equal to 0, then that would mean 2x is greater than or equal to 1 and x is greater than or equal to 1/2. That's the domain for just g. But once we put g in the denominator, we now also know that the denominator cannot equal 0. If we try to figure out when does the square root of 2x minus 1 equal 0, you'd square both sides, but 0 squared is 0. And you solve that equation. That's still going to give you x cannot be 1/2. What's happened is it's taking away the or equal to in that g domain. It can still be greater than 1/2, but now we're saying x cannot be 1/2. So that domain would be an open circle at 1/2. And we're going to shade to the values greater, which are to the right here. And we write this as the domain of f divided by g is parentheses 1/2 to infinity. In the next video, we'll look at how do we evaluate these function operations.